Okay, technically there's nothing going to be new in this video, but we're just going to combine two things that you've already learnt on this course, and that is combining the partial fractions right at the beginning of Year 13 Pure and the content we've just been doing with some integration. So just to remind you, a partial fraction is something that perhaps looks quite generally like this. We have some kind of polynomial on top, and then perhaps some roots all factorised on the bottom. There's a dot, dot, dot in there. That can be written as something over x minus x1 plus something else over x minus x2 plus something else over x minus x3, and so on. Just keep going until you've got all of these roots. The condition of that is that the order of the polynomial on top has to be strictly less than the order of the polynomial on the bottom. So for example, if the bottom has got 3 roots, then the top cannot be more than quadratic. If the bottom's got 5, the top cannot be more than a quartic, and so on. If it is, then you can adjust this by adding extra constants to the end. But generally, a question will kind of guide you through how to split something into partial fractions. Also, if you have repeated roots, so let's say, for example, we've got p of x divided by a into x minus x1 times x minus x2 squared. So this is a repeated root on the bottom. Then we deal with that slightly differently, and this is all covered in the partial fraction theory back at the beginning of the course. So that'll look like that. And again, a question will kind of guide you through that most of the time. And when you're asked to integrate something like this with respect to x, then we can just integrate each of these with respect to x, which are fairly straightforward because most of the time the top is the differential of the bottom, or at least can be adjusted to be the differential of the bottom. This one, it wouldn't follow that rule because they've got a quadratic on the bottom, we've got a constant on the top, but we can use the other special case in my previous video to integrate that fairly quickly as well. So the point is, once you've split it into partial fractions, it becomes very quick to integrate, which is the whole purpose of doing so. Just to remind you of some standard partial fraction forms. This one you definitely need to know. Just split it out into 2 fractions. It's just a linear divided by a quadratic. This one you definitely need to know on the old spec. I can't remember if you need to know on the new one or not. But if you've got a quadratic factor which doesn't factorise any further, then you need to have a linear on the top, on the numerator. And if you have a repeated root, as I just said, you split it out into the single and then also a separate double as well. Okay, so I've just got 2 example questions for this, and that will finish this video. So we're asked to integrate this with respect to x. We can't integrate that as it is. There's no way to make the top the differential of the bottom because you've got a constant on the top and a quadratic on the bottom. So we're going to have to do some kind of algebra manipulation first to get this out. So what I'm going to do is I'm going to use partial fractions on this. So I'm going to say the integrand, that's the contents of the integral. So this fraction is the integrand. I'm going to say this is identical to something divided by 5x plus 1 plus something else divided by 2x minus 1. And the way to get that something is to use the partial fraction idea, multiply both sides of the identity by the denominator on the left, and I get 7 is identical to a into 2x minus 1 plus b into 5x plus 1. And then you can either plug in 2 values of x, get simultaneous equations, or plug in 2 values of x in such a way that they cancel and you just end up with a linear in a and a linear in b, or you can equate the coefficients. Whatever method you choose, doesn't matter. I like equating the coefficients just because it's a bit more vigorous mathematically. So looking at the power of x to the 1, I've got 0 on the left-hand side because there's no x. And on the right-hand side, I've got 2a plus 5b. And then looking at the coefficient of x to the 0, I've got 7 on the left, that's the constant terms, minus a and plus b on the right. So I can go ahead and solve these simultaneously. However method you choose doesn't matter. I'm going to do that plus 2 times that because I get rid of my a's, and that'll give me 7b equals 7. So therefore b is going to be the number 1, and a therefore is going to be -6, but that's not right. Oh, because I did 2 times that. Yeah, there we go. There's a 2. So I did that plus 2 times that, so it should be 0 plus 2 times 7, which is 14. So I get 7b equals 14, so therefore b is 2. And if b is 2, then a is -5. There we go. Okay. So that tells us then that the integral can be written as the integral of these two fractions separately. So let's put the -5 there, divided by 5x plus 1 dx, plus the integral of this fraction, which is 2 divided by 2x minus 1 dx. And we can see that the top, in both cases, is the differential of the bottom. If I pull out that minus, I'm just going to put minus there, change that to a plus. So that's going to be equal to the negative of the natural log of the mod of the bottom, 5x plus 1, plus, and again, the top is the perfect derivative of the bottom, so I don't have to do anything there, the natural log of the mod of 2x minus 1, and then don't forget your constant of integration. With these questions, it's not uncommon to then be able to combine the logs together. So we end up with the natural log of the mod of 2x minus 1 divided by 5x plus 1 using some simple log laws. Okay, that's the answer. Example number 2. Okay, slightly different. It's got a different partial fraction to deal with. So what I'm going to do is, again, it's going to split it out into partial fractions. And in this case, it's going to be ax plus b divided by x squared plus 4. Okay, because that quadratic doesn't factor out any further, so I can't split it out into 2. So I have to put a linear on the top. And then I've got this linear factor, which is going to be another constant divided by 2x minus 1. Now, if I take this identity, okay, the integrand is identical to that, and I multiply it by the denominator of the left-hand side, I'll end up with an identity, a quadratic identity. 5x squared minus x plus 12 is going to be identical to ax plus b times 2x minus 1 plus c into x squared plus 4. Okay. And again, I quite like equating the coefficients of this. So I'm going to have the coefficients of x squared. On the left, I've got a 5, and on the right, I've got 2a plus c. And then the linear term, I've got minus 1 on the left. I've got 2b minus a on the right. Okay, there's no c, there's no linear term from that one. And then the constant term, I've got a 12 on the left, and then I've got a minus b plus 4c on the right. Okay, so these have to be true, and I've got a set of simultaneous equations here, which I can go ahead and solve. And what I'm going to do for this is I'm going to use my calculator for it. So you can go to equation mode, and the smaller Casios have this function as well. So equation mode, and it'll come up with this menu. I want 3 unknowns because I've got 3 unknowns here, a, b, and c, and this will allow you to solve a set of simultaneous equations, linear simultaneous equations. So the first equation is 2a. So I'm going to say x is a, y is b, and z is c, and then these are the coefficients. So the first equation is 2 times a plus no b's plus a c, and that must equal 5. My second equation I've got minus a, I'm adding 2b to it, there's no c's, and that's going to equal minus 1. And then finally, the third equation, there's no a's, I've got a minus b, I've got 4 c's, and that's going to equal 12. And the calculator will be able to tell me what the answers to those are. So don't forget, x was a, y was b, and z was c. So therefore, a is 1, b is 0, and c is 3. Okay. You could solve them manually, but it is a bit more effort when you've got 3 of them. Right, so now I've got those 3, I'm actually going to integrate ax plus b, but a was 1 and b was 0, so that's just x divided by x squared plus 4 dx, plus c over 2x minus 1, but c was 3, so that's plus the integral of 3 over 2x minus 1 dx. And these are 2 integrals that I can just carry out fairly easily, because I can make the top of the differential at the bottom here by timesing by 2 and timesing by 1/2. And again, I can make the top of the differential at the bottom by timesing that by 2/3 and then timesing the whole thing by 3/2. Okay, and I'm doing that, so I'm timesing the integral by +1, so it doesn't actually change the integral, but now the top of the differential of the bottom within the integral. So I can say that this is going to be equal to 1/2 times the natural log of the bottom, which is x squared plus 4, plus 3/2 times the natural log of the mod of the bottom. Didn't need the mod here because that's always positive. Plus your constant of integration. And then we can combine the logs in this case as well. I'm going to pull 1/2 out times the natural log of the mod of x squared plus 4 2x minus 1 cubed plus c. Okay, and that is the answer. What you can do with both of these answers is you could actually write, I'm going to do this in green, you could actually write the plus c as a plus log k instead, and that will allow you to pull it into there as well. In fact, in this case, if I do plus 1/2 log k, again, that's still an arbitrary constant, then I can write my answer even more succinctly and say it's 1/2 times the log of the modulus of some constant k times x squared plus 4 times 2x minus 1 cubed. Okay, so the plus c has now been pulled inside the logarithm as a multiplicative constant as opposed to an additive constant. This has its advantages. Everything is inside the log, so it makes it a bit easier to deal with. And sometimes a question will have this as an answer. It will be show that this integral can be written like this, and you'd have to kind of bring that constant in to the log. Okay, cool. Right, thanks for watching.